So it is a pleasure and an honor to have Marc Henneaux to continue the series of Balzan lectures, and especially about this burning problem, those times of the BMS structure, now seen at spatial infinity, or rather at null infinity.
Okay, well, thank you very much. Thank you very much for the invitation. It's an honor also for me to be here for the Balzan lectures. And so indeed, I will talk about the BMS group, but viewed at spatial infinity and how we can connect it to what is known about at null infinity. So perhaps what is striking about the BMS group is that it's infinite dimensional, where naively one would have expected, when one studies the asymptotic symmetries of the gravitational field with a vanishing cosmological constant, to find the Poincaré symmetries, the symmetries of the background. But the group is much bigger, it's infinite dimensional, and that makes it, in fact, quite interesting. Even though I think initially when this was discovered, it was thought of as some sort of embarrassment. I mean, people did not really understand why one would get this infinite dimensional group. Now, since then, other examples are known. For instance, in three-dimensional gravity with anti-de Sitter boundary conditions, we don't get just the anti-de Sitter group in 3 dimensions, but the infinite dimensional Virasoro algebra, and which is another example where the asymptotic symmetry algebra is strictly bigger than the symmetries of any background. Okay, so as I said, initially the BMS group was, or the role of the supertranslations, which correspond to this infinite dimensional enlargement, the physical role of these extra symmetries was not very clear, but with the work of Strominger, one can say that the BMS group and the BMS supertranslations have been given physical life, since they have been connected with soft theorems, the memory effect, and so as infrared properties of the gravitational field, and that really paves the way to flat space holography, although flat space holography is still to be constructed. So the question I would like to discuss in this talk, in this lecture, is how to see the BMS group at spatial infinity. So initially in the work of BMS, the group was identified at null infinity, but somehow one would like to, if it's a symmetry of the theory, it should be seen also on space-like hypersurfaces, on Cauchy hypersurfaces, which have the whole information about the theory, so in particular about the symmetries. So if the BMS group is really a group of symmetries, it should be seen on space-like hypersurfaces, which means at spatial infinity as well, since they go to spatial infinity. But when people studied the asymptotic properties of the gravitational field at spatial infinity, at least in the early treatments, there was no sign of the BMS group. I will review that in a few transparencies. But so there was a tension between the results found at null infinity and those found at spatial infinity. And somehow people thought that then perhaps the BMS group is only something that you can see at null infinity because it's tight, it's connected with, strongly connected with gravitational radiation, and that's why people have not seen it at spatial infinity. But as I said, if a transformation is a symmetry of a theory, which in a sense the work of Strominger has shown, because you have worded entities related to these symmetries, so they are indeed normal symmetries, well then it should be visible in any formulation. Maybe it's more complicated, but at least it should be visible. And so I will show how to exhibit the BMS group at infinity, and then I will discuss further developments. But first I want to explain how to see the BMS group at spatial infinity, because the answer indeed is positive. One can exhibit the BMS group at spatial infinity, and the reason why there was a tension between previous works at spatial infinity and null infinity results is that implicitly in the boundary conditions that were imposed at spatial infinity, there were coordinate conditions that were too strong and that were actually freezing the possibility to make BMS transformations. And then because you were gauge fixing something that you should not gauge fix, the people did not see the BMS group at spatial infinity. In a nutshell, this is what I want to explain, at least in the first half of the talk. I will show that indeed with more flexible boundary conditions, which can be consistently imposed, we can get the BMS group at infinity, so namely the boundary conditions will be invariant under these BMS transformations. The BMS transformations will have canonical generators and charges, and we can compute the algebra of these charges just as we can do for any other symmetry.
Will you prove that there is consistency with PDE rigorous mathematical definitions of solutions?
Okay, consistency I will define consistency within the Hamiltonian framework. Okay, but there must be connection, but I will not be that rigorous. Okay, or I will not try. I'm not saying it's not rigorous, but it's not that I will not try to show it how rigorous it can be. Okay. But so once you have these more flexible boundary conditions, and we can actually relate them also, I will show, to what people do at null infinity, there is consistency between the two analyses, okay? Which I think is reassuring, and it also means that we can do on spatial hypersurfaces analysis of BMS transformations, etc. Okay. So this is what I would like to explain, and then I will, as I said, work on space-like hypersurfaces, and what is well adapted to that study will be Hamiltonian methods, because I will relate charges to symmetries using standard Hamiltonian techniques, and the other charges will generate the symmetries through the Poisson bracket, and I will then discuss this a problem which has been known for a long time, but somehow has been discussed in the literature more recently again, which is how can one define an angular momentum which is invariant under supertranslations? And I will do it actually using the algebra. So once I have the algebra of the generators, well, I will show how this can be done. Okay, so as I said, I will work with the Hamiltonian formulation of general relativity, and so a central role will be played by the gravitational action, but written in Hamiltonian form. So they will be, so as we know, we have the special metric will be the Q, so these are the canonical variables. Its conjugate momenta Pij is related directly to the extrinsic curvature of the hypersurfaces t equal constant. Okay, so these are the canonical variables defining phase space, and then there are constraints, and the constraints are implemented by Lagrange multipliers, the lapse and the shift, which multiplies the so-called Hamiltonian constraint and the momentum constraint. And then if we are working on a space with boundary or a space with a region at infinity, there might be a surface term, and actually I will discuss a lot this surface term, but there will be a surface term.
Everything will be in 3+1.
Well, I will do that in 3+1. If I have time and if I remember, I can say things about higher dimensions. Okay, now these are the Hamiltonian constraints in 3+1, so otherwise the factor here would be different. Sorry, here. So this is the Hamiltonian constraint, which expresses that some quadratic expression in the conjugate momentum plus the spatial curvature of Gij should be equal to 0, and the momentum constraint that the covariant divergence of pi should be equal to 0. And as we know, the Hamiltonian constraint generates displacements perpendicular to the constant time hypersurfaces, while the momentum constraint generates displacements parallel to the constant time surface. Okay, so this is really old work by Dirac and ADM, Arnaud Deser and Misner, and the emphasis on the boundary term and how to construct a boundary term is Reggie and Teitelboim. Okay, so, but I will discuss the boundary term. But in order to discuss the boundary term, you need to discuss first, to give first the boundary conditions. And actually this will, I mean, this really completes the definition of what you call biphase space. I should tell you how Gij, how pi ij, if there is an region at infinity, go to 0 or do go to something as you go to the boundary or to infinity. Okay, this is something that you need to do to complete the definition of the theory. And so I will have to give boundary conditions on Gij and pi ij. And this is what I meant by consistency. I want the boundary conditions to be such that any configuration that obeys the boundary condition should make the action finite. Okay. And well, since I'm working in the asymptotically flat context, I would like my boundary conditions to be at least invariant under Poincaré symmetry. So the metric and the extrinsic curvature should approach the metric and the extrinsic curvature of flat space, of Minkowski space, in such a way that the boundary conditions will be invariant under the Poincaré transformations. At least that one. Maybe they will be more, and they will be more, but this is a minimum requirement which I put into what I call the consistency requirements. And let me tell you how we can, I mean, let me give you boundary conditions that fulfill that, these conditions.
Okay. And saying the action is finite is equivalent to saying the variation, all variations would be such that the variation...
Yes, okay. So the action should be finite for all configurations that obey these boundary conditions. So the variations should also keep the action finite, which is, I think, a very... And why do I ask this? Well, not only because I think that the action is something very important, but it's also because the action is finite. Then we will have in particular a finite kinetic term, so the symplectic form, which derives from the kinetic term, will be well defined. We will be able to introduce brackets, which are well defined, compute Poisson brackets, etc. And I will have the Hamiltonian formalism well defined. Now, usually what people do, and I will... So this is somehow the historical approach. Well, people assume, and it's very natural to assume that because we know what is the elementary solution of the Laplacian inspired by that in 3+1, so we assume that Gij, like the potential, goes like 1 over r to the flat metric, which I call delta ij in Cartesian coordinates. And the extrinsic curvature, if you compute it on solutions like, well, Schwarzschild, it's 0. But if you compute it for Kerr, or if you take Schwarzschild and boost a slice of Schwarzschild, you will generate a non-zero extrinsic curvature. You can show that this will decay as 1 over r squared. So it's natural to, and this is what people did, to assume that the extrinsic curvature, so the conjugate momentum to the special metric, goes as 1 over r squared.
But in PDE, usually one assumes stronger Gij goes to Schwarzschild for the 1 over r piece.
Yes, I want to be more flexible. Okay, yes. And I think probably one can be more flexible also in the rigorous treatment of PDE. So I think, okay, I want to be...
Okay. But the BMS group will not be hidden in the non-Schwarzschild 1 over r. We'll see.
I don't... Well, it could be that they are fixing somehow the possibility to make BMS transformations. This, okay, I cannot have...
You can fix things. Do they really exist? That will be discussed.
That will be discussed, because precisely I will argue that one cannot fix them. Okay. But yeah, that's of course an important question. But so let me go on, and I will tell you at some point why we cannot fix what I will let. So now, actually, just this requirement, and I think this one... Just this requirement, without further condition, is too flexible. And this you can already see just by looking at the action and the kinetic term of the action. If you look at the kinetic term of the action, this goes as 1 over r squared for generic configuration. This would go as 1 over r So this is 1 over r cubed, but you get an r squared when you integrate here. So you get dr over r, the leading term, dr over r. So you will get a logarithmic divergence of the action. So something should be done if you want to eliminate this logarithmic divergence. And what people have observed, and this was done by, I think first, but maybe Thibault will correct me, by Regge and Teitelbaum, was to observe that one way to kill that divergence is to assume that the coefficient of dr over r is equal to 0. This you obtain by integrating over the angle, the coefficient of dr over r, the leading term in pi ij and gij. So if this is a knot function on the sphere, that integral will be 0 and there will be no dr over r term. It will only start dr over r squared, but that's convergent. And so the logarithmic divergence will be absent. So this is what Regge and Teitelbaum imposed. They imposed that the leading piece, and this will be on the next slide. So they imposed parity conditions. And I will say a few words. They imposed that the leading piece of the deviation from the flat metric should have some definite parity, and if you want to include Schwarzschild in that set of configurations, you take it to be even under the antipodal map. So n is a normal, so and n going to minus n is the antipodal map on the sphere, and pi ij will then be taken to be odd. Now this clearly kills the divergence, odd to leading order, huh? So you don't say anything about the subleading terms. You only restrict the leading order because that's what controls the leading divergence, the divergence. Okay, now you could say that this is somehow consistent, and that was actually one motivation for imposing these boundary conditions. You can show that they are invariant under all Poincaré transformations. So they are invariant under translations, that's very easy to check, but also under boost and under rotations. So from that point of view, they fulfill the two requirements I expressed. But these strict parity conditions, so I will call them strict because, well, they fulfill the parity conditions on the nose. These strict parity conditions leave no room for the BMS group. And why is it so? And that will give me the opportunity to say a few words about the Hamiltonian formulation. Well, if you do the computation, which I will explain, you find that the asymptotic symmetry group is just Poincaré and not more.
Marc, are you going, since the word symmetry appears many times already, are you going to define what you mean by
symmetry?
Symmetry versus symmetry.
Okay. So asymptotic symmetries are symmetries. Okay.
So why do you say that asymptotic?
Okay, I will let me. So first of all, they are symmetries. So that which for me means they leave the boundary conditions invariant, they leave the action invariant, and because they leave the action invariant in particular, they are canonical transformations. Why do I call them asymptotic symmetries? Because as we will see, they will always be the generator will be the sum of a bulk piece which is proportional to the constraints plus a surface integral. And when the constraints all, or if you work modulo the constraints, which we know this is gauge invariance, we should identify two functions that are equal when the constraints all. The only relevant information is really in the surface integral at infinity. So it's really the asymptotic information which is relevant, and this is why I call them asymptotic symmetries. But they have a standard canonical, Hamiltonian generator that you can actually obtain by Noether's theorem if you want. The only thing is that the interesting piece of that transformation is the asymptotic part. Differently put, in the bulk there will be diffeomorphism, which we know are physically irrelevant, but asymptotically they will be sometimes people say large diffeomorphism on improper gauge transformations with a non-vanishing charge, and I will argue that then these ones should not be, or you should not take the quotient by these ones.
And all those charges are supposed to be measurable?
Well, let me first define them. Then I ask the experimentalist to do that. Okay, well, some of them, yes. I mean, the mass, the angular momentum. Okay, let me, and then the memory. Actually, some of these charges will be related. I will explain, okay. Which I think is in principle measurable. Okay, let's go to that. Okay, so as I said, you can ask, what are the diffeomorphisms, what are the gauge transformations that preserve my boundary conditions? And they will be generated by some bulk contribution proportional to the constraints. This will be the parameters of the diffeomorphisms, or sometimes people say that since you think in terms of 3 + 1, you are deforming the hypersurface. So this would be the normal deformation. This would be the tangential deformation. So you look at diffeomorphism, and the generators will take this general form, that preserve the boundary conditions. Now, I have written to you the boundary conditions, so you can ask what are the coordinate transformations that preserve them. And you find that there is, of course, the homogeneous Lorentz transformation. You can check that. But I will focus which blow up like R at infinity. But then you have also order 1 transformations. And my claim is that arbitrary angle-dependent order 1 transformations that I will have to submit to parity conditions preserve the boundary conditions. So you might say, oh, this is good because these are functions of the angles, infinite dimensional. So let me say that. So I'm saying that if you make a transformation, I will write the transformation rule of the canonical variables in a second. But if you make a diffeomorphism, which is of order 1 at infinity, so it's a function of the angles, so of the unit normal, it will preserve the boundary conditions. Because the boundary condition, you can show that to leading order, well, this is a diffeomorphism, spatial diffeomorphism in flat space. So this is the Lie derivative of the flat metric with Fi, okay? That will be, if this is of order 1, its derivative will be of order 1 over R. So that will give me a variation of delta ij, which is of order 1 over R. But there will be parity conditions that I will come back to in a second. And then you can show that the variation of the conjugate momenta under diffeomorphism, this you have to do some work, but you can compute, to leading order is given by the second derivative of that normal deformation. Well, so there is a di dj, and then there is a flat space Laplacian with delta ij, up to corrections which are of lower order. So under diffeomorphism, which takes this form, this is how the transformation, these are the variables transform. And you can show again, see again that if perp is of order 1, you take 2 derivatives, you will get something which is of order 1 over R squared, which is the order of pi ij. So that preserves the boundary, at least the order of the boundary conditions. But now you have also to impose parity, you have to remember that your boundary conditions are defined also by parity conditions. So you have to tune the parity of f perp and fi in such a way that the leading order of hij and the leading order of pi ij have the requested parity properties. Now you can see immediately that if hij is even, you take a gradient, that should be, fj should be odd, plus a constant. So this would be the general solution that fulfills, is compatible with the boundary conditions, including the parity restrictions. And for pi ij, if this is odd to leading order, this is a leading order contribution, you see that f perp, where is it? No, here, f perp, yes, is the sum of a constant that will drop again, plus a function that should be odd in order to preserve the parity condition. So of course the constants are even, but so you see that the only even piece which is allowed are constant, and then we can have an arbitrary odd function. So you might say, oh, we are in the good direction because we get parity conditions which are preserved by an infinite dimensional symmetry group, because it's parametrized by functions that depend on the angles and which, apart from having these parity conditions, are arbitrary. So this is an infinite, I mean, all the odd spherical harmonics you have to include for J perp, for Ji. But my claim is that...
Assuming ij Teitelbaum the strong pi things at this stage.
Yes. At this stage, yes. So I'm showing why with these parity conditions it doesn't, I mean, we don't get BMS, okay? Yeah, so and this is...
Understand, you are trying to find some transformations which map solutions to solutions, and somehow, because they're diffuse, but somehow they do not decay at infinity.
That's right.
And if you find some, then you consider that it's a symmetry.
Not yet. Well, it's a symmetry, yes, but it could be a gauge, a trivial symmetry, a gauge symmetry.
Yeah, well, what's the criteria?
Let me come to the next slide. Well, it's good. That means that I am being followed. So it's good. Yes, then the criterion is actually you compute the generator, and if the generator is non-vanishing, is not equal to 0, it means that it defines a non-trivial symmetry. If the generator is 0, it defines a trivial symmetry. Why? Because in the quantum theory, for instance, the ones that are 0, you will have the trivial representation. The other ones, you may have non-trivial representations if the corresponding charges are not 0. So if the charges are 0, they only allow the trivial representation, which means that the group is trivially realized. So it's not very interesting. It's only when it can be non-trivially realized that it's interesting. And what determines that is the value of the charge. If the charge can be non-zero, then it can be non-trivially realized. So let's compute the charges. And so the charges are computed like ADM, and Reggie and Teitelbaum have shown a direct way to determine the surface term that has to accompany the bulk. So the generator is always given by the same type of bulk piece, which is a combination of the constraint. And then the asymptotic behavior of psi perp and psi I, if they don't go to 0, you need a surface term to make the generator well-defined as a canonical generator, make well-defined functional derivatives. And this is the criterion that determines the generator.
Uniquely.
Sorry?
Uniquely?
Up to a constant. But this is the standard. We know that the generator of a transformation, if I give you the transformation, the corresponding charge is determined up to a constant, because a constant has 0 bracket with everything. And so and sometimes there are nice ways. I mean, for instance, here we would say, let's choose a constant so that Minkowski has 0 value for all the charges, which is natural choice. Then it's uniquely determined. If you say the background should have 0 value of the charges. Then you compute that, and you know, is it?
At the end, you would be saying that diffeomorphism transformation of Minkowski, which I would still call Minkowski, is different as a physical spacetime.
I think I would, if the charge is not 0.
Yes, just to understand where we go.
Yeah, so I would say also that if you take Schwarzschild and you make a diffeomorphism transformation that doesn't go to Poincaré, but BMS, you will get a different solutions. But in a sense, I would say it's the same thing as if you take Schwarzschild and you boost it. Well, it's an equivalent solution, but it's not the same solution. A moving thing is not the same as a non-moving one. And somehow we have the same phenomenon with the BMS charges. Okay, maybe I think, yeah, that will be, in a sense, it's the crucial point. Okay. Okay, so here you compute the charge, and I said there is a standard recipe for doing that. Actually, the charges look very much like the ADM charge and the ADM linear momentum. The ADM linear momentum would have here the constant part, I mean, because you make constant translations, and for the energy, this would be 1. And then you recognize the expression for the ADM energy and ADM linear momentum. This is the DeWitt supermetric of the flat space. This is the surface element on the sphere. This is the normal. And well, just to check that the boundary conditions make this surface integral finite, this goes like r squared. This is of order 1. And this is of order 1 over r squared, because the leading piece is 1 over the r. You differentiate 1 over r squared. So this is a finite surface integral. Here also, this is 1 over r squared. This goes like r squared. So this is a generically finite surface integral. However, the claim is now that the odd part of the symmetries that I wrote on my previous slide completely drop from the surface integral. So you only see in the surface integrals the even part. Why is it so? But that's because this is clearly odd, hij to leading order is even, but I take a derivative, this is odd. So if I have odd, odd, and here also odd, when I integrate over the sphere, I get 0. So the only piece that will survive in the integral is a constant. Same here. This is odd because it contains a unit normal. So when I make the antipodal map, it changes sign. This is odd, that was the restriction we imposed. So I'm claiming because this surface is even, only the even piece of fk will be seen. And the even piece is the translation part. The odd function jk drops. And so out of this infinite dimensional set of transformations that leave the of diffeomorphisms that leave the boundary conditions invariant, only a finite number is physically relevant. Because the other ones, they have a 0 charge. They can really be thought of as standard diffeomorphism, even if they don't go to 0 at infinity. The fact they have 0 charge it is as if they were going to 0, and you can consistently factor them out because they are in the trivial representation. But the other ones have, in general, non-vanishing charges, and so they define physical transformations.
Can I ask an elementary question?
Yes.
The charge is associated, so according to this formula, it's associated to the solution that you started with and to this functions f, which is the transformation. So the charge is a function of what?
So the charge is a function of q and p, of the canonical variable. So not only on, so it's not only defined on solutions. It's actually, you can view that as the initial condition. So maybe. Okay.
But why does it depend on f's that start with?
Because the charge depends also on the parameter of the transformation. So for each transformation, I have a charge. Okay, f is really
saying this is like the moment map. I mean,
yeah, it's a moment.
Yeah, I don't understand why the charge is associated to.
Well, then you could factor.
It's just noted here, like the energy, as we know, is associated to time translation. Delta t is MC.
That's right. It's a delta. So it's multiplied by the parameter of the transformation.
Okay.
It's just the Hamiltonian way of saying.
Of writing things, yes.
Yeah, just to recall the terminology. It's been a while since
So the charge will depend on the transformation, and I have kept the parameter, and on Q and P. But indeed, normally one factor out then the parameters, and that's the moment map for each initial transform in a generator. We have a charge, okay, but it has some index. Huh? Okay, so I'm contracting the index with the parameters in the way of writing.
It's in the co-algebra, the dual of the algebra.
Exactly, yeah. Okay, so as I said, so I'm using here the terminology that was introduced by Reggie Teitelbaum and others. So if I look at a gauge transformation, in this case diffeomorphism, which have 0 charge, then they are called proper gauge transformation because it's legitimate to take the quotient by them. If they have non-zero charge, they didn't use the terminology large gauge transformation, some people do. I will use instead the terminology improper gauge transformation in the sense that they don't correspond to a redundancy, to the physical redundancy in the description of the system. Okay.
But Tullio Regge would have said this is very satisfactory.
That's right.
So you're going to extend that.
Okay. So
did Claudio say yes? Title
okay,
yes, so I'm convinced, or he would say, why extend?
Well, he worked also on BMS and trying to get the BMS in Hamiltonian, so I think he would be convinced. But indeed, it's true that for a very, very long time, many people, including myself, were very happy with this result because no one knew what to do with the BMS group. So it was somehow an embarrassment to have the BMS group, and here we don't get it. So, okay. But then comes Strominger, and he tells us the BMS group, you can associate, you can define word identities to the symmetry in the standard way that you associate. We have charge, you can define, I mean, it will commute with the S matrix, and you will have word identities. There will be theorems coming out of that, which are the soft theorems. So somehow you relate it. these symmetries that no one wanted to look at to physical things that people knew.
Yes, but he also said there are infinitely many conserved charges.
Yes.
And this I could never see, nor Gabriele, what they mean, those charges in a real scattering situation.
No, but they are, you have a, okay, let's...
At the end, when you have now infinitely many charges...
How will you measure them? Okay, this I'm afraid...
Real theorems, constraints, real things. Okay.
I think so, because these are the soft theorems, no, for the BMS charges. Okay, let's...
Is there since 1965.
Yeah, and actually, one of my motivation here was to derive the soft theorem like in the old days, namely you are defining, you use word identities and you define the S metric on space-like hypersurfaces, and you sandwich it with, I mean, e to the minus, and then you take the limit and you see what happens. This is why this, I mean, this was one of the motivations. Okay, but then, and I think we will probably again discuss that. You see, the point that we wanted to make was maybe we don't see BMS because we have fixed too much implicitly through the boundary conditions. The boundary conditions are expressed in terms of variables which are not invariant under diffeomorphism. So when I give you boundary conditions on Gij and Πij, implicitly I'm telling you things about the coordinate system, because not any coordinate transformations will preserve the boundary condition. So you are somehow fixing part of this diffeomorphism. And it could be that that some of the diffeomorphisms that you are fixing are improper, namely have a non-vanishing charge, and you have fixed something that you could not fix. Now the only way to tell is to see whether you can release, compute the charges, and see whether they are zero or not. Okay, this was our philosophy. Suppose someone tells you, well, after all, Poincaré charges are conserved. I can always go to a frame in which the momentum, the force momentum is along the time axis and the angular momentum is along the z-axis. Then I compute the invariance group of these boundary conditions that always fulfills this. I will say, oh, the symmetry group is time translation times SO3. You don't see Lorentz if you fix boosts. So we thought that maybe we are fixing BMS without realizing it in the same philosophy. So the same philosophy. Okay. This is what I said. So where are the BMS supertranslations? And the philosophy is really that at least we can see the BMS group if we go with with boundary conditions which are not as strong as a strict parity condition. So we say that with these strict parity conditions, clearly we are killing the even part of Fperp and the even part of Fk, and the claim is that this is precisely where the supertranslations are. And so because we have fixed the supertranslations, clearly we don't see them. I mean, we have gotten rid of them by making too strong a coordinate fixing at infinity. So let's relax these parity conditions. But of course, we don't want to relax the parity conditions too violently because they were imposed in order to keep the action finite. So if I just drop them, I'm back to the problem that the action is not finite. So I have to keep some version of the parity condition, which is not the strict version, but which is still sufficiently strong to maintain finiteness of the action. And the idea, in a sense, is extremely elementary. We just allow a specific term in the metric and the conjugate momentum, namely a term that is generated by a coordinate transformation which has the opposite parity. So if I take even f's and even fk's, this is forbidden by the strict parity condition because they will generate terms which are diffeomorphism transformation terms which do not fulfill the parity conditions. The idea was say, well, let's allow them and see whether we can keep going. So let's twist the parity condition, but only by a diffeomorphism. After all, if you are working with quantities which are not gauge invariant, that seems to be something which is reasonable to do. Sometimes you say, in electromagnetism, I will fix the vector potential up to a gauge transformation. So here we will fix Gij and πij up to a diffeomorphism that will have the opposite parity as the ones that we have shown. Okay, so this is the idea. And so that we will enlarge the class of diffeomorphisms that we can make at infinity. Okay, this is just what I said, but of course we have to write the diffeomorphism in terms of the canonical variables. And so, well, let me just give you the idea. I don't want to spend too much time on the technical aspect, but so I will add, so Gij is the Regge-Teitelbaum part with strict parity condition. I will add to Jij a term which is generated by a coordinate transformation. Okay, and since, well, I can always absorb the even part here, I will assume that this is purely odd, which means that I will take that to be even. Okay, then that will be purely odd, and that's okay. I will allow that in the boundary conditions. Now, in fact, so this is what we call the twisted. We are twisting the strict parity condition by a piece that comes from a diffeomorphism of order 1, so that we are preserving the 1 over R behavior. Now, actually, we have to be slightly more restrictive if we want consistency, which consistency meaning also that the boost, we want the boost to be defined by, to be canonical transformation, so to leave the action invariant. It turns out that we have to be slightly more restrictive. We cannot allow an arbitrary diffeomorphism Zi to twist the boundary conditions, but it has to depend on a single function of the angle. And since this is even, so it has to be the gradient of a function of a function like this. And since this is even, that function should be odd. So I don't want to go into the technical detail. I can give you the references if you want, but consistency of the formalism restricts, if you want, Lorentz invariance, in the sense of Lorentz invariance of the action, the form of this twisting that way. It's simpler for the momenta. And so Uij will be the second derivatives of Ru. Okay, for the momenta we do the same. We take the strict parity part, I mean, which is odd, the Regge-Teitelbaum boundary conditions, but we twist them by a diffeomorphism, but written in Hamiltonian form for the conjugate momenta, which takes that form. I wrote it for you, so remember for psi, we had psi perp. Okay, now I take a particular psi perp, which I call V, and this is what it is. And since Pij is odd to leading order, this should be even. I mean, the odd part I can always absorb. So without restriction, I can assume it is even. 2 derivatives, so I can assume that V is even. Okay, so it's the same idea there. And now I ask the question, okay, so in the end I get a twisting by 2 functions of the angles, the even function V that characterizes the twisting of Pij, and the odd function that characterizes the way we twist the boundary conditions for Gij, the metric. Now of course, since I relax the boundary condition with respect to the strict parity condition, you might still ask, is the action finite? The answer is yes. Do we have well-defined generators for the Poincaré transformation? And with the boundary conditions I've written, the answer is yes. These are technical things, so probably I don't go over them. It requires some work, but I think the idea of the new boundary conditions is very elementary. Now you can show that you have to, well, to complement that by some strict technical assumptions, that you have to impose that the constraint should all faster at infinity, but this is not a very big thing than what is dictated by the decrease of the canonical variables. And also you have to impose some stronger conditions on the mixed order there. Okay, but this is technical. I can give information later if you want. Then the question is, we have now boundary conditions. What are the diffeomorphisms that preserve these boundary conditions? Now, of course, by construction, because I allow this twisting piece, I have more diffeomorphisms that preserve it. But the real question will be, what are the charges? Are they zero for these things that we are now allowing? Are they non-zero? Okay, so again, you see that all the boundary conditions are preserved by Lorentz boosts. So this would be the tangential deformation corresponding to a boost. Sorry, the normal deformation corresponding to a boost by Lorentz by rotation, spatial rotations, and then also preserved by order 1 diffeomorphism that takes that form, and that can be, well, there is the odd part and the even part as before, but this is not interesting. We are interested in T even and W odd because that gives us an even Wi. So these are, we have now a wider set of transformations that preserve the boundary conditions. Okay, this wider set actually, the zero mode indeed is a translation. The first spherical harmonics would correspond to the spatial translations, and the zero mode would be the time translations of T. But we have more transformations. The question is, are they relevant or not? Well, I didn't write the charges. Maybe they are written later, but I am anticipating here. Actually, you can integrate the equations from spatial infinity to null infinity, and I will give an idea of how this is done in the second lecture. And you can connect the even function t and the odd function w, which appear here, with which defines these order 1 time deformations and space deformation. By integration, you can connect them with the function alpha of the angles that describe supertranslations in the null infinity description. It's not just the sum. It's more complicated. You have to integrate equations, but morally, it's like the sum. So you see supertranslations are described by an arbitrary function of the angles in the null infinity description. Arbitrary functions means that there is an arbitrary even part, an arbitrary odd part. Up to some transformations, you can connect even and odd. Okay, that's, you have to integrate some equations, but it's not conceptually difficult. But what is important is that these symmetries, parameterized by this larger set of functions, are canonical transformations, so you can compute the generators. The generators are given by a bulk piece which vanishes due to the constraint, but then there is a surface term, which is really the interesting part. The asymptotic part is the interesting part, and you find that it is non-zero. Okay, it's generically non-zero. For instance, if you look for the supertranslations, I've written things in polar coordinates, but that's in spherical coordinates, but that's equivalent. You find that again it looks very much like the ADM energy and the ADM linear momentum, but now I have written things in polar coordinates. T is not 1 here, it's an arbitrary even function of the angle. Well, when it's 1, you get the ADM energy, but you get other things when it's not 1. And generically, this will not be 0. And W will give you the linear momentum and also a part of the supertranslations. When it's first spherical harmonics, it gives you the linear momentum, but higher odd spherical harmonics will give you higher supertranslation charges. And this is generically non-zero for arbitrary T and W, fulfilling the parity I mentioned. So we do get non-vanishing charges. So the reasoning is, since we get non-vanishing charges, we cannot, by a gauge transformation, set them equal to 0. We cannot go to a frame in which we freeze the possibility of making BMS transformation, because BMS transformations have a non-vanishing charge, so we should also allow non-trivial representations of these extra transformations. It's not the trivial representation as you have to do for strict gauge generators.
If I have initial data, like the Brillouin-Puig space with two Schwarzschild, two wormholes, do I get in ordinary coordinates? Do I get non-zero charges here? Okay. Or they are all like the sum of two Schwarzschild have only mass?
That I cannot answer. I think it's indeed an interesting question to have natural solutions, because of course you can always cook cook up a metric with non-vanishing.
So saying if I take Schwarzschild and I do a twist in the coordinate.
Yes, this I will get
non-zero.
This I can see from the BMS algebra because I know how the chart transforms.
I have Schwarzschild in ordinary.
No, then you get 0. But you say, yes, but I would say then, and if you have Schwarzschild in this stress frame, you have no linear momentum and you have no, this is the argument.
There is something in the argument.
So sorry, I didn't get that. Does Schwarzschild, after some transformation, you get a non-trivial charge or not?
No, Schwarzschild, if you take just Schwarzschild, the only non-vanishing charges are the mass, I mean the P0.
In ordinary
coordinates.
You show how to twist the...
Yes, so even I can...
So it's a Schwarzschild solution, yes, from the GR point of view, but now with non-zero.
Exactly, I can do that by twisting. Yes. And I know indeed that the transformation rule of the... Yeah, I know how things transform under the algebra, because I can compute the algebra, which is what I want to show here. These are diffeomorphisms, but as a boost is also a diffeomorphism. Yeah. Sorry.
Charges are conserved.
Yes, they form an algebra. They form an algebra, and actually they commute with the Hamiltonian. Yes, because the supertranslations commute. It's an abelian, infinite-dimensional abelian algebra. But they don't. They do transform in the boost, just like P mu transform in the boost. I mean the
conservation in the yes.
Yeah, then they will.
Okay, they won't be conserved on stripers because.
No, that's right. So, but I'm at spatial infinity. Okay, I will come to that. Okay, now as I said, you can match. You can compute the algebra. I will probably. I think I have only 5 more minutes, no, or something like that. No, no, until 4 o'clock. Ah, that's right. Okay, okay, we are fine. Yeah, you can also match the generator because people have written, okay, the generator now, what does that mean? The matching with null infinity is really when you take the limit of things as you go to the past of future null infinity. So this is where we do the matching, because then of course the charges are not conserved along null infinity, but so you have this. I will draw that again in the second lecture, but so I don't want to connect them. There is spatial infinity here, and so it's a Penrose. Yeah, this is in the Penrose diagram. So as u goes to u retarded time goes to minus infinity, you are going. This is where how you want to match things with spatial infinity. But you might say, indeed, is it of any interest because it's strictly conserved in all processes? So how do you? Okay, let me.
Also, because there are recent papers of Abai, who for years would have been happy to say BMS exists. Now he says, no, I have only one guy. No, but he says more, because this is linked with recent things. Like the shear that you choose Poincaré by taking that the limit of the shear of the metric, the waveform at minus infinity nu, should be gauged to be 0.
Yeah, and that actually is absolutely equivalent to taking strict parity conditions at spatial infinity. So Ashtekar would now go to Regé Teitelboim.
Except that I would totally disagree with this.
And also disagree with him. So he's he's changing his religion somehow. Yes. Yeah, I agree. Yeah, but since the parenthesis has been open, actually is the condition that he imposed that the shear should be 0, the potential for the electric part of the shear should be 0, and this I will say exactly in a second, is equivalent to asking strict parity conditions. So if you don't want it to be equal to 0, you have to buy the twisted parity conditions.
No, but if I want it non-zero, then even Einstein 1916 would say it's non-zero, but parity, but still electric. Okay.
Electric, yes. I'm talking about the electric part. So the magnetic doesn't play any role. Whether it's 0 or not, you don't mind. Okay, in fact. Okay. But so and this will be the second lecture. I will say more about the matching with null infinity. Maybe this should be viewed as a parenthesis. Okay. So the algebra is interesting if you can just compute the Poisson bracket of the generators, which is represent the algebra. And what you find is if you take 2 of these BMS transformations, psi1, psi2. The Poisson bracket will be another BMS transformation with parameter psi hat. So this is the way I write the algebra.
Will that be impossible that they don't close, or is it guaranteed once you say the action is preserved?
I think that if the action is preserved and you have not, you could have central charge, okay? Because we know that we have a projective representation. And this is related to the fact that the generators are always defined up to a constant. And maybe there is no way to adjust the constant so that there is no central charge. In this case, there is no central charge. Okay, so it's a, but you might say, perhaps I forgot some symmetries and that they will reappear here. What you know is that the bracket will always be a symmetry. Now, if you have a complete list of all the symmetries, then you know it will close. But suppose I know that we have boosts and rotations along the third axis, then I start playing with commutator, I will find, oh, I forgot that there are also rotations about the other axis. Okay, but here we have all the symmetries. I mean, at least it forms a closed set. It's a Lie algebra in this case. And, well, I've written it in some strange form because it's adapted to polar coordinates. But so these are the killing vectors on the sphere. So they describe, so you take two killing vectors on the sphere. They describe the spatial rotation. These are the boosts, which are described by a function of the angle because I am considering, this function, and this would be the super translations as I described. And I want to tell you that the super translations transform non-trivially under rotations. Well, they transform as functions on the sphere, so this is fine. You see, this is the Lie derivative of a function along the killing vector defining the rotation, but they get mixed, just like P0 and Pk get mixed by boosts. And it looks complicated, but this is just equivalent to the known transformation rule of the super translations on the boosts. And it's interesting to see that because B has a definite parity, W also, and they have the opposite parity as T, so everything is consistent and works nicely, and you can check Jacobi, everything works. Okay, maybe now the question raised by Thibault. I have twisted my parity conditions by terms that involve two functions, u and v. And indeed, the big question is, how do I know that I cannot set u and v equal to 0? Now, I would say, from the Hamiltonian point of view, I cannot, because they correspond to non-trivial. This would need a transformation with no non-vanishing charge, and I'm not allowed to gauge fix such transformations. But maybe there is another physical meaning that one can give to them. And actually, this is done by observing how u and...
If some PDE person comes and say, if I take these initial data in this, but then when they evolve, their boosted thing does not satisfy this anymore, except if they are more restricted, this is not excluded by what you're saying. Because in principle, the evolution of Einstein equation is constraining things, no? More than...
Yeah, I would... That's right. I would think that what they do can probably be extended to this case because, after all, these are diffeomorphisms, and we know that the equations are invariant under diffeomorphism. It doesn't mean that they are trivial symmetries, but they are... Okay, now, these functions u and v, which induce a twist, which defines a twist, transform very simply under super translations. They are just shifted. And so they parameterize, well, that's of course by construction. They parameterize the super translations that you need to do to go to the frame in which they obey strict parity conditions. But the reason, so I said it's physically legitimate to impose strict parity conditions because this is an improper gauge transformation, but there is also another physical reason that I can invoke, which is precisely related to what Thibault was saying, and which is related to the boundary shear. Now, if you connect these, so u and v are defined on a space-like hypersurfaces, but you can integrate the equations and you can to connect with null infinity. Okay, and you can ask the question, to what component of the metric, let's say in the boundary frame, in the boundary coordinates at null infinity, would this u and v lead to? And actually they combine exactly to form, I mean, because they have definite parity conditions. C as an, I mean, at null infinity people don't impose parity conditions. So they combine even odd to form the null infinity potential for the electric part of the boundary shear, which I did not write. So CAB is defined by second derivatives on the sphere of C, some combination.
But here you mean the value at minus...
So at this, yes, here, yes, because then it evolves.
The memory, which is measurable, is the difference between the shear there and...
Okay, but then I will... Okay, let me complete my... Okay, first I say that. Okay, then with this I will come to the memory. So I did not explain on the slide, but then I will... okay, let me... Now, we know that under supertranslation, C is shifted, which is exactly that. If you want to... So if you want, of course, it's shifting the C. If you shift by a supertranslation here, C, that would amount to shift U and V to which connect to that C by W and T. Okay, so far, okay. Now, why do I say that this is related to the memory effect? Because, after all, there is no detector at null infinity, and there is no detector at spatial infinity. We have to look at practical detectors, I think. No, just a second. Yes. So I think that to find... Okay, why is, you might say spatial infinity is absolutely not interesting because everything is conserved, nothing happens. I can go to the rest frame at null infinity and that's it. Why is the ADM? The ADM energy is strictly conserved according to ADM. But of course, in real situation, you are not at infinity, there is no observer, but you are in a region where you can assume that you can use these asymptotic expansions.
But the conservation of ADM means if I do a different slice, space-like which goes to infinity, it has the same mass.
No. What I'm saying that ADM is conserved if you take into account all the energy. Okay, that's fine. But people will say sometimes you want to see how the mass inside some that you are observing has changed. And I think it's useful to use ADM as well. I mean, you can say I'm computing ADM before.
So it's called bonding. It's the bonding energy.
Yeah, it's just, but there is a matching with ADM. That's why it's okay. But your detector is not at null infinity. It follows. I think it follows even a time-like trajectory.
Let's not talk about detectors. Let's talk about.
Okay, so what I'm saying is that if I now look at a situation which is more realistic, and I assume that initially U and V are 0, and I can use these asymptotic expansions, and then a wave goes through. During the time the wave goes through, these asymptotic expansions are not valid anymore. I think the parity conditions will be more violently changed, because there is no reason for things here to be the wave to be exactly antipodally equal to what is going in the opposite direction. Maybe you will not buy that, but let me go on. And so you cannot really assume that the parity conditions, strict parity conditions, will be obeyed during the process. But after the wave has passed, if you wait for a while, you will again be able to use ADM techniques to compute the mass of what is inside. But I'm saying that the value of U and V will have changed because it's connected to alpha. And so if it was 0 initially, it will not be 0 after that. And actually this is just the memory. We know this is the memory effect. We can discuss that more if you are not... But this is, I mean, I'm saying that, you know, the wave never goes at spatial infinity in any case. So if you want to take into account the memory effect at spatial infinity, you are never going to see it. So, but on the other hand, I don't think the universe is not asymptotically flat. So, yet it's useful to talk about as isolated systems. And the quantity that we define, like the ADM energy, which is defined as spatial infinity, is useful even in that context. I'm saying that the other guys are also useful to the same extent. Okay, this I...
Usually people use this argument on square plus and they say...
I think it's equivalent.
That's why the super translation are really there, because after a gravitational wave, you are...
Yeah, I think...
You are just doing this at finite r.
That's right, but if you really look at the... I think that at finite r, exactly. But so if I am at finite r on a space-like slice, it's exactly the same. I think it's the same argument. I'm not... but you know, so if the argument is accepted at null infinity, I think we should accept it at spatial infinity.
But if I don't accept it at null infinity, I was...
Ah, you don't want... Ah, okay. Ah, no. I think it's equivalent. Okay, at least for the moment. Okay. Well, I have this argument that the charge is not zero.
Yes, that's what I wanted really to understand.
Okay. Yeah, so then the question that you will ask, and you know, the good thing here is that we can define charge. We have a symplectic structure which is well defined, and we have a moment map. And so it makes sense to say that the charge is the generator of the transformation. At null infinity, it's more complicated because they are dealing with things which even the symplectic form is not conserved. So how do you relate a charge to a transformation is more complicated. Here we have techniques.
And for Maxwell, there is the same story.
Yes.
Infinite number of new charges.
Yes. Yes. Yeah. Which are precisely the angle-dependent U1 transformations. Okay, so I'm saying that, of course, it's the same argument. So if you don't buy it in what version, I'm sorry, yeah, and I cannot provide a more stronger argument. But I'm saying that U and V change when a wave will pass. Okay, now the algebra, and I will have to speed up a little bit probably, but so let me stress the ideas. There was some feature of the BMS algebra. You might say it's just a feature, but it was a bit embarrassing, I think, at least for some, or intriguing, say, of the BMS algebra, that it's not a direct sum of Lorentz with supertranslations or of Poincaré with supertranslations, but it's a semi-direct product, which means, well, you can expand. This is what I said already. But in particular, if I okay, let's look at the structure. I don't want to go into the technical details, so let's just look at the structure. I denote the homogeneous Lorentz generators by MA, so this includes boosts and spatial rotations. And then I have the standard translations, which I denote Ti, and the super translation S alpha. They are an infinite number. Now, if you look at the algebra, which I wrote, but now let's say symbolic or in more concise terms, well, this is just the Lorentz group. Translations form a semi-direct representation, non-trivial representation of the boost, so we have a semi-direct product. This is Poincaré. And then we have the super translations. They commute with the translations and among themselves, but they transform non-trivially under the Lorentz transformations. They form a non-trivial representation of the Lorentz group. And actually, they even, well, it's not, they also contain translation part. Okay, we have this set of transformation. Now, if I look at this commutator, which tells me that the super translations form a non-trivial representation of the Lorentz group, so they transform under Lorentz transformation, I can view this Poisson bracket in the opposite direction. That tells me that the Lorentz generators transform under super translations. Okay, the Poisson bracket is antisymmetric, so this tells me how S transform under M, but that also tells me how M transform under the transformation generated by S, super translations. And so the angular momentum in particular will get some trivial commutation Poisson bracket relation is classical. And so that means that the angular momentum will transform under supertranslations, okay? Just as it transforms under translations. Now, under translations, no one, well, this is something that we know very well. If you change the point with respect to which you compute the angular momentum, it changes. So you have to look at the intrinsic angular momentum if you want to get something invariant. Okay, well, this is what I said. Okay, so I was anticipating. So I'm taking about one of these intriguing physical features which result from the algebra.
It's not a preferred Lorentz subgroup.
And there is no preferred Poincaré. Yes, this is, yes, yes. This is related to that, yeah. So it's the same problem phrased in different ways. But so people, well, some people rephrase that as ambiguity in the angular momentum, supertranslation ambiguity in the angular momentum. You might say it's just a feature, but it's a bit, since we don't know how to deal with that as we can for ordinary translations, you might say this is a bit an ambiguity that we don't know how to control, because in which frame should I compute that? Okay, this is the one, okay. The other intriguing features were precisely what you said. Okay, so this is the question. Can we have a better definition of the angular momentum that would be invariant under supertranslation? And the solution has been suggested by different groups, okay, how to construct such an invariant angular momentum. It was done at null infinity by various groups. I mean, a group by Yao and collaborators, another one by Porati and collaborators, another by Comparet and collaborators. And there is another solution at spatial infinity that was given independently, but it is really equivalent when we compare, when we integrate, as I said, and compare the limit of what they do as u goes to minus infinity, and compare with what we do at spatial infinity.
But does it boil down to saying you want to fix the infinite past value of the shear to be 0?
No, not necessarily, no. But I will keep, in a sense, I will keep track of the initial value. And I will, I mean, maybe this, well.
Because you know there is this thing with the gravitational scattering and the discussion with Gabriele.
So I don't think it's equivalent to that, but it's a way to keep track of the initial value. I will, because you will have the supertranslation charges appearing in the redefinition. But let's just look at the problem. Can I redefine an angular momentum or something that is not invariant? Can I redefine it in such a way that it is invariant, whatever it is? And I'm saying that because we have these functions u and v, which transform so simply under supertranslation, they are just shifted. We can always use them to compensate any variation we don't like. Just the idea in a line. I mean, this is the main idea. Suppose I have a quantity A that transforms under supertranslations in this way, non-trivially. It's a representation, so it will transform linearly with some coefficient, alpha and beta. Now, I'm saying that if I correct A by terms that involve u and v, I can cancel that. Well, I might need, okay, that's obvious, because when I compute the variation of A, I'll get this. When I compute the variation of these terms, assuming alpha and beta to be invariant first, I can clearly cancel this term. Of course, you might need higher order terms if alpha and beta does not do transform. In our case, they don't. And so that's it. Well, actually, they do, but okay, I will give you the formula. So the idea is that to apply this recipe, since we have the supertranslations, and since we have these functions u and v, which are related to the shear, which shifts by supertranslations, we can use them to define a new angular momentum, which is invariant. Okay. And so that you can show it's equivalent to the redefinitions that people do, at least in that limit. Now, you might say, what is the meaning of the idea of doing that? And in particular, you see, you will redefine the angular momentum, by adding terms. Then you will ask, what are the transformations that these new angular momentum generate? Are they rotations? Or is it still, I mean, you are redefining the generators just by this requirement, but do they still form an algebra which is isomorphic to SO3? Does it make sense to ask what transformations they generate on the canonical variables? And, well, the second lecture is shorter, so maybe what I will do is I will flash the result here, and I may come back to that at the beginning of the second lecture. Yeah, so I'm saying, so I want to see what U and V generate. Do they generate, what do they generate? So can I compute the Poisson bracket and just see what they do? Now the Poisson bracket, because they are just asymptotic values of field, it's complicated to define. You have to know how to extend that in the bulk. And we claim, well, one thing that we did, so that we come even with more super translations, is that if we freeze still a little bit more the boundary, unfreeze, sorry, the boundary conditions at spatial infinity, by allowing, let me first state the results before you ask questions, by allowing logarithmic diffeomorphisms that blow up at infinity but in a logarithmic way and in some controlled way, but just by two functions, this can be done. Okay, this is what I said. I'm claiming that these functions U and V, if you want to see what they generate, you have to allow transformation of coordinates which involves a logarithm, and this is what they will generate. Okay, this I can come back to that after the break. I'm not going to give all the technical details, but you can design boundary conditions which are even more flexible than the ones I wrote, and in which when U and V are well-defined generators and will precisely generate these more flexible new coordinate transformations that are allowed, and that they are of logarithmic type. You know, it's like, okay, so they will involve logarithm of R. I mean, so they still go, I mean, the metric and the conjugate momentum still go down to go to zero at infinity, but in a much slower way. And so these are controlled by one odd and one even function. And somehow we don't see that if we don't allow these more general diffeomorphism, it's a bit like, suppose I have a canonical pair, QP, and I want to see what is the action of P. And suppose that somehow you have set Q equal to 0, here the logarithmic supertranslation is equal to 0. Then of course you don't know what is the action of P, because it shifts Q and goes out of Q equal to 0. So to see what is the action of P as canonical generator, you have to allow arbitrary value of Q. So we say that the situation is somehow the same. If we want to see what is the canonical action of U and V, we have to allow diffeomorphism of a more general type, but still diffeomorphism, still coordinate transformations, which are these logarithmic supertranslations. And then we can have a consistent description of the theory with these more general boundary conditions. We can compute the charge, and the charge are not 0. Of course, you might say that maybe the game never ends, but why not R, diffeomorphism proportional to R, etc. We could not go beyond, but that doesn't mean. But so the nice thing you see is that U and V, so again I'm writing the charges with the parameter of the gate transformation times the generator. So I'm contracting the indices, which here amounts to integrate over the sphere. And so they are the generators of these more general coordinate transformation. And once you have this canonical description, well, you can immediately see what the new Lorentz generators generate. So if you have this algebra, you can compute the algebra of with the logarithmic supertranslations, L alpha. They are conjugate, it's like Q and P. They form pairs. And so by improving the MAs using L and S, which are conjugate, you can kill this term, just as I showed, not this one, this one not, of course. This is just the Poincaré. No, sorry, you can kill this one. Not this one, of course, but this you can kill. And this you can kill by redefining M to an M tilde that commutes with S and L. So let me show you the formula.
You have a formula for the angular momentum.
Which is a new form. Yes, here it is. Yeah, we have written the integral, I mean, all the indices, so you are making quadratic redefinitions of the angular momentum by term proportional to the BMS translations, BMS charges, and these are the logarithmic charges, but of course the logarithmic charges are just u and v, so even when you have set, I mean, they are still non-zero even if the logarithmic supertranslations are set equal to 0. If you want to make them act, you need to allow logarithmic supertranslations, but it's not because you have set q equal to 0 that p is equal to 0. So this, okay, so we have a quadratic redefinitions of the Lorentz charges, which means that we are going out of the Lie algebra framework, but that's fine because the charges really form a Poisson manifold, a natural context. I mean, if I have a charge which is conserved, any function of the conserved charge is a conserved charge. So when we have a Lie algebra, it's nice, but really the proper framework is the one of Poisson manifolds. So you can make quadratic redefinitions. And so that means that the new Lorentz transformations will be, okay, so this is what we can, by this redefinition achieves that goal. So we will have a new angular momentum and new boost generators that will be invariant under supertranslations, and also about with respect to logarithmic supertranslations. This probably you didn't care about, but this is a crucial relation. And this bracket does not suffer any modification, and you can show that this redefinition also preserves all the Poincaré algebra actually. So yes, they are extract term, but they can't, I mean, in the bracket they form exactly what they should. So the claim is that this new angular momentum does not suffer from the supertranslation ambiguity. What does it generate? Well, if you compute the bracket of anything with m tilde, it will generate the ordinary transformations that you know, plus what you obtain by taking the bracket with this. Taking the bracket with this will generate a translation and supertranslation with a term proportional to the supertranslation generator. But then they will also generate, when you compute the bracket with L and L, a logarithmic supertranslations with a parameter equal to the BMS supertranslation charges. Because it's quadratic, so the bracket will involve two pieces. Okay.
Voilà pourquoi votre fille muette.
Sorry? Yeah, I'm going over time. I'm sorry for that. So in the end, you have completely decoupled the BMS supertranslations and the BMS logarithmic supertranslations from Poincaré, which in a sense is really a version of Darboux theorem because you have conjugate pairs. So once we have that, we can always decouple other functions from L and S. So it's really a weaker version of Darboux theorem. And so let me...
There is a preferred Lorentz subgroup, Poincaré subgroup.
Well, it's not. No, I need to extend and then to make quadratic redefinition. So I'm really I'm looking for it in the enveloping algebra. So that's why, I mean, so the theorems that people have demonstrated are correct, but it was within the context of linear redefinitions. And with linear redefinitions, you cannot get rid of that ambiguity. But if you allow quadratic redefinitions, which allow these, the generators are just the BMS generators, and this memory function, well, if I can call them memory function u and v, then you get something which for not only is supertranslation invariant, but also still close according to the Lorentz algebra. So from that point of view, they generate Lorentz, I mean, an algebra isomorphic to Lorentz, or Poincaré even. So it's fine from the algebraic point of view. Yeah, this is what I said. But so let me perhaps just go to the conclusions. Well, first thing is that by enlarging the boundary conditions, we can get agreement with the analysis at null infinity. The BMS algebra is really a symmetry algebra on space-like hypersurfaces. We didn't see it before because we froze somehow illegally the possibility to make BMS transformation, but if you relax the boundary conditions, and I even argued, even though it was a bit in a rush, that one should relax them even more, by diffeomorphism of a very specific type and still allow for a canonical description, this is what I mean by consistent, then you get a description in which you can redefine the Lorentz generators so that they are supertranslation invariant. Now, just to conclude, one can also do the same for electromagnetism. You have also an ambiguity in the Lorentz generators due to this angle-dependent U1 ambiguity, because these angle-dependent U1 transformations do not commute with the Lorentz algebra, and so they transform in some non-trivial representation of the Lorentz group, which means that the Lorentz generators do transform under angle-dependent U1 transformations. But by making a similar redefinitions, you can get an angular momentum which is independent from them. And with this, I will thank you. Yeah.
Questions or comments?
I have a short question.
Question?
I've always learned to impose conditions also on the derivative of the metric and the thing. So is this parity something more general, or?
I think it's different. So you might say, how does it compare, for instance, with the Lorentz gauge, or the Donder gauge, I should say, which involves derivative of the metric? Is this? When you
impose asymptotic conditions, you just say metric 1 over r, momentum 1 over r squared. So what I've always learned is that for some integral we do need derivative.
Okay. So I'm sorry. Okay. I have been a bit sloppy. So very often when I say a function is of order 1 over r, I'm assuming that the derivative, if I need the derivative, is of order 1 over r squared. Okay. Yeah. This was implicit. Okay, I should have said. I'm assuming that there is no violent sine r squared, for instance, variation. Okay. So, and I don't need it all the way. So probably I need that for the first derivative and the second derivatives for the metric, I think. Probably.
Yeah, but for the same argument, one needs then more derivative for the angular momentum.
Okay, now the angular momentum is finite without boundary conditions. Okay, that was actually one motivation of Regge and Teitelbaum. They didn't really care about the symplectic structure, but indeed the angular momentum, if you don't impose some sort of parity, something at infinity, the angular momentum will linearly blow. The linear momentum is finite, so if you come with a vector that has an extra power of r, you would expect things to blow up. And they impose these parity conditions, and that made the angular momentum finite. But it turns out that when we relax the boundary conditions, we have to strengthen the constraint at infinity, and that also plays the same role of making the angular momentum finite. Using the Killing equation for the Killing vector on the sphere.
Okay, we should stop now to have tea so that we can have a break before starting again in,
yes.
in 20 minutes.
20 minutes. Okay.
Okay, thank you
Thank
again.
you.